Welcome to today's Explainer. We are diving straight into an absolutely incredible breakthrough from researchers at UMBC and Cornell that uses light instead of electricity to run artificial intelligence. If you've been following the massive power demands of modern AI, you know we're hitting a literal physical wall. So today, we're exploring a paper that proposes a mind-bending solution, replacing electrical currents entirely with photons.
Here is our roadmap for today. We'll be looking at the AI energy crisis, computing using only light, the sub-photon breakthrough, some real-world hurdles and caveats, and finally, what this means for the future of AI hardware. Let's get into it.
Can we run artificial intelligence on literally less than a single particle of light? I know, it sounds straight out of science fiction, doesn't it? But keep this question in mind as we explore how researchers are pushing the absolute quantum limits of physics to perform complex deep learning math. We aren't just talking about using a little less power here. We are talking about operating at the fundamental shot noise limit of detected photons.
Section 1. The AI energy crisis. Why Moore's Law is struggling.
So let's start by understanding this massive, frankly unsustainable energy wall that modern deep learning is currently slamming into. A staggering 80 to 90% of the cost in large-scale commercial deployments of neural networks actually goes to machine learning inference alone. You see, there's this common misconception that training the AI is the only huge energy sink. But in reality, once a model is out there in the wild, the continuous, everyday cost of running it, that inference phase, completely dominates the balance sheet.
To put that into perspective, our conventional digital processors, standard GPUs and TPUs, are consuming tremendous amounts of energy just to execute the millions of basic mathematical multiplications these models need. Every single operation takes between 10 to the negative 14th and 10 to the negative 12th joules. Now that might sound tiny, but when your deep neural network requires billions of these operations every single second, well, that energy consumption rapidly spirals into something completely unsustainable.
Section 2. Computing using only light. To escape this energy trap, researchers are looking away from traditional wires and turning toward the physical properties of photons. The crucial thing to understand here is what an optical neural network actually does. It physically replaces electrical currents with light beams to do the heavy mathematical lifting. In deep learning, the most computationally intensive operations are matrix vector multiplications. An ONN fundamentally computes these abstract operations as a physical phenomenon, meaning the math is essentially solved at the speed of light, just by shining a beam through a medium.
And get this, to prove this works, they didn't even use some exotic multi-million-dollar laser array. They literally used an everyday OLED smartphone display as their light source. Yes, basically the exact screen you have in your pocket right now. The green pixels on the display represent the input data. That light then passes through a spatial light modulator, which physically adjusts the intensity of the light to represent the neural network's weights. The optical math actually happens in two distinct physical steps. First, as light from the OLED passes through the modulator pixels, it performs element-wise multiplication. It's essentially just light being dimmed. But step 2 is where the real magic happens, the optical fan-in. They use a single lens to physically focus all those individual light beams down onto one single bucket detector. This physical focusing inherently sums up all the light, performing the complex addition part of the neural network instantly and completely passively.
Section 3. The sub-photon breakthrough.
Now this is where things get truly wild. The team pushed this optical fan-in technique to an almost unbelievable extreme. Because they are summing up massive arrays of spatial modes, we're talking vectors up to 500,000 dimensions at once, the combined light hitting the detector is bright enough to be accurately read, even if the individual beams are incredibly weak. By doing this, they proved you can read the classic MNIST dataset of handwritten digits with 90% accuracy using less than one single photon per multiplication on average. Specifically, just 0.66 photons. The math checks out because you don't actually need a whole photon per path. You just need enough total photons hitting the lens at the very end to read the sum.
Breaking down the results, we can see exactly how this scales up. Operating in that extreme sub-photon regime at 0.66 photons, the chip hits that 90% accuracy. But when they increase the light just slightly so that 3.1 photons are detected per scalar multiplication on average, the network accurately classifies 99% of the digits. That matches the exact accuracy of a digital computer running the exact same model, but it's achieved purely through optical, shot noise limited hardware.
The energy implications here are absolutely staggering.
To achieve that 99% accuracy, this optical setup used a mere 230 femtojoules of total optical energy for an entire inference task. That includes all the matrix vector multiplications for a single pass through the neural network. Now compare that to the digital electronic equivalent, which requires roughly 10 to the negative 8 joules per inference. The optical calculation uses vastly less energy for the entire network than a standard electronic processor uses for just a single floating point multiplication.
Section 4. Real-world hurdles and caveats.
All right, let's take a step back. While the lab results perfectly prove the theoretical physics, it's not quite as simple as ripping out your GPU tomorrow. Hardware engineers rightly point out a massive distinction in how we actually use AI. These photonic chips are phenomenal for inference, meaning running a model that already knows what to do. But training a model from scratch? Totally different beast. Training heavily relies on complex feedback mechanisms and backpropagation. Traditional GPUs are literally built for this, but optics struggle immensely with those complex feedback loops. So, photonic chips won't be replacing those giant, energy-hungry training clusters anytime soon.
Plus, as the hardware community is quick to highlight, we can't ignore the input-output penalty. To get data into the optical chip in the real world, you have to convert electrical data from a standard computer into light, and then convert that light back into electrical data at the detector. And guess what? That conversion process has an energy cost. If we aren't careful, the energy loss during that translation can heavily eat into those theoretical efficiency gains we saw in the pure optical math.
Section 5. The future of AI hardware. But hey, despite those valid conversion bottlenecks, the hardware architecture of the future is almost certainly going to be a hybrid. Why is this hybrid future so promising? Well, because the vast majority of our everyday AI usage relies purely on inference. Think about audio denoising, image enhancement on your phone, running voice recognition, or generating a block of text. Those are all inference tasks. Deploying specialized optical chips right alongside traditional processors just to handle these specific, high-volume workloads could save just an incredible amount of power across global data centers.
Even when hardware analysts factor in that electrical to optical conversion overhead we just talked about, the long-term projections are still wildly favorable. Researchers estimate that a full-scale optical system, where the optical energy is just a fraction of the total system power, could still consume around 10 to the negative 11 joules per inference. That is orders of magnitude less total system energy than today's absolute state-of-the-art electronic accelerators and custom silicon.
Which brings us to our final thought for today's explainer. As traditional chips literally start overheating and maxing out their physical atomic limits, are we witnessing the crucial moment where the baton of computing progress is finally passed from electricity to the photon? It might not happen overnight, and it'll probably start with specialized inference accelerators, but the physics is crystal clear. Light offers a path forward that electrons simply cannot match. Thanks for joining me on this deep dive, and definitely keep your eyes on the incredible world of photonic computing.